I'm very delighted that our first ASOR Melbourne talk from Adelaide is being given by Axel Bender from DSTO. So Axel's sitting down here. You guys can see him, and I haven't yet found out from Axel how he went from doing a PhD in theoretical particle physics to working in operations research type problems. So that might be my first question for him afterwards. But for now, I'm just going to hand over to Axel. Take it away.
Well, thank you. Thank you very much for the invitation. Well, thank you to you. And Fred, I believe I have to thank as well, because he has been pushing for me to come across here for quite a while. I'm also particularly pleased because the work or the talk that I'm giving today on degeneracy-based design is actually one of those rare occasions where when you do operations research, so something that's more an analysis kind of environment where you apply a lot of methods that potentially many others have developed, you come across something that has such a vast applicability across a whole range of disciplines and a whole range of problems that it is really very exciting and something that is really worthwhile sharing. So I'd like to talk today about degeneracy-based design, and it is something that relates to systems engineering more so than operations research. However, I came across it when doing operations research, so therefore I will start to give you at least the motivation that got us to that discovery, and then explain three or so concepts that are relevant in this design space that I'm talking about, and then ask a question, namely, which is one that probably many of you have come across, namely how to measure or demonstrate some of those ILITs, non-functional requirements that very often relate to the evaluation of systems, or in particular complex systems. Before I then take a long time as the bulk of this talk, give you insights in how we went about measuring adaptability and robustness in a particular example, and in this operations research problem. Then I will mention that many times before that anyway. You will notice that the model does actually not rely at all on the context for which it was developed, which makes it so applicable to a lot of things, and in that generalization I'll hint at least to a series of applications and potential and opportunities in a vast array of disciplines that where this is applicable. Anyway, I mean, so the problem that we faced, and this is a while ago, I mean, you see in brackets 2007, and actually predates this, is the Australian Defence Force had for a number of years a project, namely that of a capability development project, that of replacing the whole fleet of what's called field vehicles in Australia. Field vehicles are 4x4 SUV type of vehicles, 6x6 vehicles, trucks, up to semi-trailers. So it's actually the whole fleet with which the Australian Defence Force undertakes logistics, undertakes some reconnaissance functions, and other patrolling functions, ambulances, etc., etc. With this new capability, or the replacement of the current capability, what the endeavor was and has been also realized is that to move from a design of vehicles where the functions of the vehicles are fixed to the vehicle, so welded into the vehicle, to one where the functions of the vehicles are in modules and shelters. And modules are fairly simply the thing in the back that you might be able to replace. And here you see a number of examples, just a cargo module, or an ambulance module, or a module where you can do command and control or other functions. So the function other than that of driving or moving the vehicle around can be separated from the vehicle and put on a different base vehicle. Now, the question that was asked at some stage that we were asked was, okay, this is actually expensive. This costs more than just welding functions to a vehicle. So at least at some stage people asked, if this costs more, well, what can you actually demonstrate the benefits of this, why we are doing this? And as we do, a lot of this was done with soft techniques because a lot of the benefits and the costs relate to fairly complex aspects, such as are there advantages in conducting a mission in terms of how reliably you can complete a mission. A mission could be a logistics mission or could be a reconnaissance mission. There's obviously things that you can also evaluate quantitatively, such as utilization of your resources, in this case vehicles. But there are other bits that are pretty hard to really decide, and I'm mentioning here the two that I like to talk about for the rest of this afternoon, namely those of robustness and adaptability. In particular, how to evaluate or differentiate quantitatively between different such design options, namely fixed versus modularized, and make really quantitative conclusions with respect to the benefits or the costs that a modularization concept would provide. Now, here, I'm sure you have encountered, or some of you have encountered this problem already. There is what is at least known by some in the systems engineering literature as the cost-benefit imbalance, which is pretty much saying that the long-term benefits of some of those non-functional requirements, facilities, are very hard to demonstrate. It's easy to calculate the upfront costs, but it's actually very hard to put numbers to the long-term benefits. Now I'll show you at least one way of how we went about this, and obviously it has been modeling, but before I do so, I'd like to make some generalizations which come with modularization, because I actually don't want to talk about vehicle modularization in particular, but as a more general design aspect of fleets and other systems. Now, what the modularization problem provides is a need to think about representations of fleets and vehicles. And, well, what I mean with representation, there is typically at least two fundamentally different representations. There's one that relates to design parameters, and what I mean there is in let's say an abstract design space, you represent your entity, your system, through some design parameters, and in a vehicle case it could be the number of wheels, how the dimensions of the vehicles, and things like it being modularized or not. But there's of course a second way, a fundamentally different way of depicting a system or a component that is what is it actually doing, or what can it perform, which I term here function space. And in vehicle it could be, for instance, that it can carry some amount of cargo. Now, what you see here, I mentioned is two spaces, but in at least this abstract space here with this dumbbell, you see represented the same entity, which is the same object. Now, why am I introducing this? It is actually a way of depicting some of those design principles. That's number one. Number two, it also will highlight the importance of this mapping of design to function, which is actually where we got inspired with respect to our research into degeneracy, which is something that is very well known in biological problems, where design is equivalent to genotype and function is equivalent to phenotype. And genotype-phenotype functions are very much discussed in literature around evolutionary, about evolution and resilience, and exactly those types of characteristics of objectives that I am after in answering this fleet modularization question. Now, what I'm depicting here now is the advantage of this representation in terms of design and function in this mapping is what I'm depicting here is, for instance, two different objects that can perform the same function. It could be, for instance, a 6x6 vehicle or an 8x8 vehicle that can both carry 5 tons of cargo. That would be an example. And this is a very well-known design characteristic, which is called redundancy. I'm adding functional in front of it. It's two different objects that can perform the same function. Now, with this space, I can also represent something different, which is known as functional plasticity, at least in the biological literature. In this case, it's the same vehicle that can performing two different functions. I will predominantly talk about function space in the future. Well, I'll also talk about the genotypes of this design space, but to depict the concept of degeneracy and others, I'm actually moving away from drawing these terrible three-dimensional things to just depicting the two dimensions. And what you then can see, for instance, the two concepts that I just have mentioned would correspond to so functional redundancy would correspond to just seeing an object in the same place. That is then something that's redundant. But functional plasticity would be something where somehow, sorry, I was now wrong. Functional plasticity, you can see when two, indeed, you can see through one connected network or one connection between two nodes, which might represent for you one object, and it shows that this object can perform two different functions, like vehicle 1 or vehicle 2 in this graph. Now, what is degeneracy? I can define it now. It's depicted here with bifunctional objects. It is a particular way of arranging functionally plastic and functional redundant agents or components of vehicles, where the observation of functional redundancy will depend on context. The important bit here is these are different objects or different vehicles or different agents that have this functional overlap in function space, because they can, under some contexts, perform the same function and satisfy, therefore, demands or requirements. Under other contexts, other circumstances, they look different. Now I'm telling you really what we did instead of answering the vehicle modularization problem, but how we, in general, looked at this problem of modularization and more. We pretty much asked this question: how can we evaluate quantitatively concepts such as adaptability and robustness of vehicle fleets that differ in the topology of their design to function mapping or genotype-phenotype mapping? And the two systems that we really contrasted was this degeneracy, where you have this partial overlap of functional redundant and functional plastic objects, and a purely redundant system, namely one as depicted here on the right, where you might have functionally plastic agents, but they don't have this partial overlap, that context-dependent overlap in how they can switch to new functions. Now, one thing I should mention before I come to the model that we implemented is what's not is I've used different colors here, but you'll see later on a depiction of these bifunctional agents where they have the same color, but sometimes the nodes of the agents are dark and sometimes they are bright. That indicates how they currently use their resources for what type of function, what do they perform. So what is not depicted here in this static picture is that this context dependent is one that is dynamic, where these agents do not necessarily perform both functions all the time, but they switch resources between performing one or the other, or more of one versus more of the other. Now, okay, the model that we've used to now get to really calculations and clear articulations of adaptability and robustness is a multi-agent system. I've used the term already when I talked about these dumbbells agents. We pretty much looked at a multi-agent system where the agents are vehicles, and we have n of them, and we make them bifunctional for simplicity, but you can generalize to functional and some agents that can perform more than just two different tasks, but for the demonstration of the concept, this was more than sufficient. The mapping that I was indicating, namely that of component to function, is captured in a matrix, which we call V for vehicle. It's representing the genotype, pretty much what is the potential of an individual agent, what kind of, we call it tasks can they perform, tasks or functions, what kind of functions can they perform. And we have m different function types or task types. If I, from this matrix VIG, I can pretty much, I get a representation, the column of this matrix is a representation of vehicle, and what a task can, what a vehicle agent can perform is pretty much genetically determined. I use the term genotype here, and we pretty much saying, if in this vector representation of a vehicle agent there's a 1, it just says, this vehicle can perform this particular task type. If there's 0, the vehicle obviously cannot. We make all agents bifunctional, which means that in this vehicle vector there's only 2 1s in there, and everyone has 2 1s somewhere. And we define now what functional redundant means, and partially functional redundant by saying fully functional redundant agents are such that when you build the dot product of these vector representations, you get 2, so the vehicles can do the same tasks, or they have a partial overlap, then the dot product is, the scalar product is 1. And if they are completely different, then obviously you get 0. Now, with this, we can now define a measure of how much degeneracy you have in a vehicle fleet. And here's the definition. Unfortunately, you can't see this, but it's pretty much a normalized way of looking at, summing over all of the pairs in your fleet and asking the question, so how many times do I get a purely partial functional redundant agent and I divide it over all the possible combination. Obviously, I've forgotten the 2 there, but well, no, sorry, I sum in it this way, so it's 1. I divide over the number of combinations, and it gets pretty much then a value between 0 and 100% as the degree of degeneracy in a fleet. Now, next part of the sorry, yeah.
So in that formula was the -1 at the very end? Is that just a copy paste error? So it's just.
Sorry, no, this is not. This is a square bracket which says. Sorry, that I didn't say that. Square bracket notation we use to say if the dot product is 1, the value of the square bracket operator is 1. If it is any other value 0, 2, it's 0, and you calculate the sum over that. So you're only counting. So you build all possible dot product of your vehicles in the fleet, and you only count those where the dot product is 1. Yeah, if it's 0, 2, yeah, then it contributes 0 to the sum, and therefore you get a value between 0 and 101 as your degree of degeneracy.
So you don't.
Sorry,
that means
that's an operator.
And so if everything is fully functional redundant, your degree of degeneracy is actually equal to 0 then.
That's correct.
It's intended. Yep. No worries.
That is intended, and that's exactly how we would determine what a fully redundant vehicle, functional redundant vehicle fleet is. So you can also say it's a fleet with 0 degree of degeneracy. And I'll depict some of those plots later with different values for this degree. Now the next thing we have in a model is scenarios or the environmental scenarios, which is pretty much in a vehicle fleet, and we are quite simple about this, your demand on the vehicles, which we define here again in a matrix. Now we have also time, and because we use evolutionary computation, time steps are pretty much discrete in our model. We also have make the following requirement on our scenarios when we actually sum over all the possible task types. We want to get we want to have the fleet fully in demand, so there's no latency or any extra redundancy in the fleet. So there's no excess capacity. So the scenarios are designed such that if the fleet is perfectly designed for this particular scenario, all the tasks can be performed. But if the fleet has some deficiency with tasks, then you pretty much have some tasks that will not be satisfied.
And are you also saying that no vehicle is unused?
That could be the case, but we do evolutionary computation, so we'll try to find the fittest, and so no, there won't be fleets in this evolutionary process that perform nothing of the scenario. But it can happen that your fitness decreases very badly. The fitness here is pretty much the difference between what your scenario demands and what the fleet can perform. So yes, it could be potentially that your fitness is pretty much minus whatever the maximum value is. What was it? Minus epsilon n, or we set epsilon to 10 arbitrarily, but so you can get values of this type. So okay, I mentioned already fitness. I mean, it's pretty much given here in this formula, but I mentioned it's a measure of distance between what demands are from your scenario versus what a fleet can provide. This particular definition, I complained to James Whittaker, my collaborator, that we define something fitness that the smaller it is, the closer to 0 it is fitter, but this is yeah, excuse me for this particular notation, that's how we published. So the smaller this value, the fitter a fleet, a multi-agent
That's a bit
system.
like obesity, right?
Golfers.
Yeah, the golfers.
I assume you can all transform in your mind. Yeah, you can. Good, and we will have a number of environmental scenarios. So fitness, this fitness here is defined for a particular scenario at a particular time. So L is an index for the scenario, of which we have a discrete number. We use 20 to 30 in our simulations, and T is just a time step. If we average over the fitness function over all environmental scenarios, we get the overall fitness of the fleet. Now, what do we do actually in the model when, let's say, there is a scenario that poses demands? We have some dynamics, and the individual agent, the individual vehicle agent, pretty much makes decentralized decisions. It looks around and looks, is there a demand that I can fulfill? And if it can fulfill it, it will perform it. And for the whole multi-agent system, we go through ordered asynchronous updating. What that means is we randomly pick a vehicle, then it fulfills the task that it can, then we move to the next vehicle and it looks what is left over. So it's this kind of way of assigning agents to demands. Now, the environment we change. Why do we do this? Because adaptability and robustness actually, as I will mention in a moment, relate to uncertainty and change. So we have a particular way of changing environment or demands, pretty much variations in tasks and task demand. Now, in our early work, we pretty much only were interested in generically seeing fitness above a certain threshold value. For the work that I'm talking about here now, we make these variations in a particular way. I'm mentioning here the two ways that we did. One we call decomposable variation, and one non-decomposable variation. It should say here volatility is wrong. The decomposable variations is pretty much we randomly pick a set of demands and order them into demand pairs. Yeah, so we have M task types. So we make M and M divided by 2 task pairs. When we then change a scenario, and we use a random walk to change, so we just increment demand by 1 or decrement by 1. When we hit one task and increase it by a value of 1, then the associated partner of that task in the decomposable variation gets decreased. That's a deterministic decrease. In a non-decomposable variations, we don't have that that kind of correlation or that kind of determinism. We actually increase a task of type J and then decrease a different one, and that one is not correlated in any way or form with the initial one. This is depicted in this graph here, where the different shades under decompose say this is predetermined. That if you change D, for instance, that then you always have to change in the opposite direction F. While if you pick D in a non-decomposable environment variation, the next decrement can be in any other. What we do though is we change the environment such that the overall demand does not change, and that the demand is always such that it's spread across all task types. We do that to actually keep the scenario dependence of the results down, strangely enough, so that we don't have to also somehow manage changes in overall demand and normalize all of this. This is all being taken care of by making these changes in a particular way. Now, I indicated here we we evolve computationally our agents. So we use initially a very simple way of genetic algorithms, at least the first part. We pretty much use deterministic crowding. We pick two parents. We walk along the loci of the vehicle, which is as of the matrix V, the function I can perform, and then with a probability of 1, assign it to offspring, but it's probability of a half that it goes to offspring 1, and probability half that it goes to offspring 2. So that's what we do with two parents. What we then do, though, is if the offspring that's generated is better than the genetically closest parent, so there's two parents, and this deterministic crowding does shuffle your genes around quite a lot, but there will be one of the parents that is genetically closer under this procedure to the other. We compare the offspring to that parent. If the offspring is fitter, we keep it. If it's not, we keep the parent. But what we do then with the offspring is actually we mutate it. And we mutate it in a way that the design principle with which we start for the fleet does not change. I don't describe to you the operator that we use for this, but it's pretty much a way of mutating particular loci, one locus in the gene, and then make sure that there will be a corresponding mutation of a different locus, such that you keep your let's say degree of degeneracy, if that's the aspiration, if you don't want to allow degeneracy to evolve, or you keep your purely redundant fleet, so that you don't generate, you don't change this degree of degeneracy. If that is, for a lot of the experiments we did, that was one of the things we wanted to do. It also means that the variations we do for different fleets that start with different designs do not bias your assessment of adaptability. So there's not suddenly the evolution generates for you combinatoric advantages of one design over the other, by doing this mutation in a more controlled way. All right, now let's define the measures other than fitness. Robustness, you all probably know there's many definitions, but the good thing about robustness definitions is that they're typically pretty close. They might vary, but the principle about it is reasonably close. I mean, it relates to invariance, with respect to some change or perturbations. I'm here quoting one definition that by Alderson and Doyle. The underlined words are pretty much telling you that your robustness measure depends on those particular inputs. Namely, you need a system. You need to define what your system is, what particular property it is that you want to evaluate. Under what type of perturbations, and how you define then what invariance means. And that's probably where then measures of robustness are different, but at the core the principle is similar. In our case, we are pretty much interested in fitness. Our system is our vehicles, the perturbations I've described. We are only for most of the graphs that I show you in a moment, interested in environmental change, but we have also done work on change, mutational change on your vehicles, and how robust your system might be to just genetic changes. And invariance is in relation to the fitness that we've defined. So if the fitness changes, then and I'll come to that in a moment. Well, actually, it's there. If your fitness changes, then you might say, if it drops, if it stays always below some threshold. We are the smaller fitness, the better. If it gets too high, in our case, and so then it might get unfit. In this case, we say this fleet may no longer meet a particular requirement. In the military, definitely, operational availability is a key measure that says we want a certain percentage of things available. That would also apply to logistics. You might want your equipment. You might want to have 90% of your equipment working, or you might want, in logistics scenarios, have 80% of your supply arrive to a target on time. So this gives you some threshold values, and against which you then can say, okay, if I now look at many different scenarios for my fleet, and I count pretty much the percentage of scenarios where the threshold, I meet the threshold value, this percentage gives me pretty much a value for robustness. Now, doing this with, as of this formula in red, namely that we ask for the fitness to be below some threshold, so that there's a threshold for unfitness, that causes problems in simulation often, because if you set the threshold too high, you pretty much don't get any any fleet can get the job done. While if you set it too low, you have failure all the time. So setting this threshold in simulation is a little bit of an art. So we use the two-tiered approach, where we first set this threshold, but then use the average fitness as the discriminator. And you see therefore in the graph values for fitness, other than a percentage of scenarios, because it pretty much went through this. First this filter, does it meet my robustness requirement, and then we'll give you as a measure of discrimination the average fitness. Again, I mention here, of course, because of this, and because of my odd definition of fitness, in the graph that you see, the smaller the robustness value, the more robust. So it's the opposite of robustness. What's that? Fragility or good adaptability. This is a bit more, or we call it evolvability, or you can also call it innovation potential, and I'll give you some reason for that a bit later. Is a bit more interesting to define. For that, I'll give you at least two definitions, one approximation to one definition which we use. The definition of neutral network, number one, is a connected graph of your genotype, phenotype, environment nodes that all have the same fitness. And connectedness in this definition of connected graph means that in this neutral network you need to be able, or every node that is in your graph can be reached through a path where your fitness does not change along that path. So this is called a neutral network. So in a fitness landscape, it's pretty much if you have if you finished off your optimization, you have your plateau, in which you might have your various different systems that are as optimal as everyone else, and this plateau would give you pretty much your neutrality network, or the neutrality area. Now this not changing at all, so equal fitness, so we really with an equal sign. It poses also again problems with simulation, so this is why often approximate neutrality is introduced, where we consider two nodes equal if the fitness value is within some percentage value if the two nodes are within some percentage. So yes, the fitness varies, but it varies only smallishly. Now, from neutral network, you can then define the one neighborhood, which is pretty much all, well, that's wrong, the all neutral, it's all non-neutral nodes, so that makes a huge difference. So all non-neutral nodes that are directly connected to a neutral network. So it's all those nodes that if you step from the neutral network out, your fitness indeed increases above your threshold. Now, adaptability with these definitions can be defined as all the unique phenotypes in your one neighborhood. And that's actually definitely from an evolvability perspective. Evolvability in biology is defined as the access to different phenotypes through variation in your genotype. So how many new phenotypes can you access from where you are at the moment? And this is where this definition comes from. This is actually one that's been promoted in the evolutionary theory literature. And this is pretty much what we did. Now you get pretty much the main finding here, namely if we compare a degenerate fleet with a purely functional redundant fleet, I mean here fully degenerate, this adaptability measure, namely the size of your one neighborhood or the number of unique phenotypes in your one neighborhood, what you see here is degenerate fleets are orders of magnitude more evolvable than are purely redundant fleets. And actually, in this particular case, I mean, I'm saying here 3 orders of magnitude. This was starting with fleets of around 30 vehicles only, and then when you generate your neutral networks, in the redundant case, your neutral networks might only end up with around 200 nodes, and your one neighborhoods maybe in a few hundreds, while with a degenerate fleet, you can see that the neutral network can be in the thousands, and the one neighborhood's then in 10,000s. But I mean, depends, of course. That kind of count, so the number that you assign to adaptability depends very much on the particular system, particular problem, and how you define it. But this huge difference in orders of magnitude between the size of your one neighborhood with the unique phenotypes in one neighborhood is one that comes up in many different simulations. I mean, here pretty much mentioned what I said already, namely, when you look at the neutral network size that you get through evolution of your vehicle fleets, you'll see that neutral networks find a lot, fit fleets and fit phenotypes, but not as many as you get with degenerate design. So there's also, you might say that there might be an application, you haven't thought of it entirely, in terms of optimization, that this actually helps you, probably find more solutions to an optimization problem than, with purely redundant designs. Now, going to robustness assessments. I mean, now here, the thing that is more or less the test of whether we have done good design with respect to our environmental variations, because what you see here is actually that a redundant fleet is better or more robust than a degenerate fleet. This is for environments where we use these decomposable variations. I mentioned on the slide that these are you can consider decomposable variations known unknowns. It's pretty much knowing what variations might lie ahead. If you know that, then actually you should be able to design a fleet that actually meets those, that can deal with those variations. that's pretty much what your evolutionary computation does, the optimization does. We start with an environment with environmental changes that are constrained to be decomposable. The fleet adapts, the agents evolve to exactly those variations, and you would hope that a redundant fleet is one that can actually maximally meet the demands, because it should be able to, because we have constrained the environmental change such that if you perfectly adapt to the change, then you should be able to meet 100% of demand, and therefore your fitness should be zero, which is the measure that we assign to robustness. Okay, so that's decomposability. Noting though, the values here, it's a logarithmic scale, and you don't know what 0.01 or 0.0001 means. Here in the next slide, you get a bit more of an impression of how much actually robustness changes. It's more in the order of 10. Because we said that the difference between demand and what the fleet can do can be up to 50. It's actually the value, the maximum value. What we have here now is how do the vehicle fleets perform, or how robust are they to these non-decomposable variations. And what you see here is actually that degenerate fleets are much more capable. So there's the flu graph is 100% degenerate fleet. It is actually again now orders of magnitude better than the purely redundant, so the red fleet. But this time probably 1 order or 1.5 orders of magnitude. Now what this tells you is that degenerate fleets are most likely more able to deal with unexpected change than are purely redundant fleets. And that's no surprise, because these purely redundant fleets, when you say I'm putting a second light bulb here into my projector, I actually anticipate the types of change that I want redundancy for, while degeneracy allows you to actually innovate, and there might be actually patterns in the change, so how tasks might be correlated. In the military, for instance, tasks are correlated. So if you treat your demands as being uncorrelated, then and you don't have a decomposable variation, then your redundant fleet would not pick up the pattern, while the degenerate fleet would pick up that pattern and therefore adjust better to those changes. Now what you see also on this graph is, the arrow should point at 3000, because that's pretty much where we did this, where we injected the shock. So manually, we're pretty much the changes in the environment, which were up to generation 3000 random walk, and only 1, 2, 3 steps of random walk over your seat scenario. At that point, at 3000, we injected a completely new scenario and looked at how quickly and how well can these fleets or the multi-agent system again adjust to this. And there's two things you see. Again, degenerate fleets do this, get back and back to pretty much the same type of robustness. And secondly, it's not pointed out more, you see that actually the fleets adapt faster. When you look at how at the slope, from fairly poor robustness to better robustness for the first 3000 generation, that slope is not as steep as what happens after the shock. So something has happened in this in the structure of the fleets, in particular in the degenerate one, that seems to cope better than with this unknown uncertainty. Now, one reason for this is for this particular robustness, and we also looked at this, and what I'm showing here, namely this network buffering principle, is also contributing to this effect in adaptability. I'll show this here. I mean, I might show you more an animation, that a colleague of mine did for me when I gave this presentation to our executive, or a similar presentation. We are here, I'm just showing a network of a degenerate system. Let's call it again a vehicle fleet in function space. So remember I showed these dumbbells in function space, and I mentioned now that there's dark and there's light nodes. So an agent that has, so these bifunctional agents, they represent, if it's dark, means currently this agent performs this task of the two that it can perform, while the light blue one it doesn't perform. Let's focus on this one and just give you a Hogan's Heroes example. Let's say there's three teams. There's in Hogan's Heroes there's people on kitchen duty. There's some that secretly build an escape tunnel, and there's another group that build a secret device. And there's a tool set that they can use. For the kitchen duty, they need knives. To dig the tunnel, they need spoons to get the dirt out. Hard work, obviously, and this device building, whatever it is, but somehow they need forks. And what you see here, they have actually functionally plastic tools. They have spokes and spikes. So devices that have a spoon and a knife end, and devices that have a fork and a knife end. Now, network buffering, what could happen now, for instance, is that, I mean, there's currently only one person on kitchen duty, and suddenly, the evil Germans, I believe, aren't they in Hogan's Heroes? Milo. Want to see more salad or so cut. So suddenly there's a shortage of agents. But building the escape tunnel is actually very, very important to Hogan's Heroes. But the device is pretty much close to ready, so they might have a shortage of people on kitchen duty, but an excess of people in device building. Now, with a pure redundant system, you could not deal with this resource reallocation problem, or you could not. Well, you would not find a solution for it. But with a degenerate system, you would, because what you can do is you can relieve one spoke from the device building, move it to use it to build an escape tunnel, and and deliberate then the spies to move on kitchen duty. So that's what network buffering is. Now that gives you an insight of why these degenerate systems might be more robust. We've also examined by changing the degree of degeneracy, etc., what the adaptability potential is, and indeed this network buffering somehow also contributes to the adaptability performance of those fleets. Now, another thing I mentioned now, pretty much, here's one more graph where you see something that pretty much tells you in the evolution. So the evolution optimizes your multi-agent systems to the demand and the demand variations. Now you can evolve, let fleets evolve such that degeneracy changes. You might end up, for instance, after evolution, that your best system has whatever 30% degeneracy and 70% agents that are either not redundant with each other or purely redundant with each other. Now, you can of course now say, hey, let's build a system that has 30% redundant, 30% degeneracy, degree of degeneracy. What you see here actually is that there is a difference between something that you evolve so that you're allowed to somehow get trained on your environmental change versus something that you then design where you just, so there's a little bit more obviously that contributes to robustness than just degeneracy or degree of degeneracy, so there must be other aspects in the topology. We haven't analyzed that yet, but that's pretty much something as an open problem. In the case of purely redundant fleets, you can see that you get no real benefit from learning out of the evolution. The two, the unevolved and evolved fleets are within error bars the same with respect to the robustness performance. Other findings that we did from looking into design is, I mean, you could ask this question, so how many agents, how many agents can you inject to actually get those benefits and adaptability? And actually, you don't need to turn every agent into a functional plastic agent. 30% about gives you pretty much the bulk of adaptability. And when you ask the question, for instance, is network buffering, how much does it actually contribute to robustness? You can actually do that also. You can run experiments where you constrain, for instance, the number of reallocations decisions by saying, let's see how much of your fitness do you generate through just one reallocation decision, how many through more. And this tells you pretty much, the analysis shows that roughly 50% of your robustness comes from this network buffering effect, which is also consistent with flexibility in biological literature. I've talked far too long, obviously, and I want to talk about the application side of it, so I'm a bit faster. So the point I want to make is, what can we learn from that beyond just vehicles? And I've already shown in Hogan's example, that the very same representation that we used in the model, you can use, for instance, in spies, but you can, or in those types of tools, but pretty much these stumbles can be any functions, and any other functions, in any system, as long as they have particular characteristics. And you can ask, so when would actually degenerate-based design show benefits, as of the model that I've represented? And there's a number of things that you can draw merely already from the model. You get benefits from degeneracy-based design. Number one, if you have some form of distributed decision making. I mean, I indicate to you that the agents make their resource allocation decisions in a decentralized way. You find that in markets, open source software, human organizations, team with flat management structure, and so on. I mean, if you think about functional plastic agents, here you get systems already, where you can see that if you go about then implement degeneracy-based design, you should actually get a benefit with respect to adaptability and also this kind of robustness to unforeseen change. Second condition or second thing that we use in the model is when you have, you're more likely to see benefits of degeneracy-based design when your agent motivation can be aligned with your overall objectives. Again, you'll find that, in some organizations at least, so some of those high performance misspelled, so some of those innovation companies, Google, etc., seem to be able to do that very well. And you might see therefore also more innovation because adaptability, namely this access to more phenotypes, is actually pretty much a way you can define, or one form of innovation, namely finding new things, innovating new things. In autonomic computing, so this is a domain that I'm working in now, at least in parts. So this is pretty much the policy is one form of autonomous, but with some constraints, namely that you give pretty much high-level guidance to your internet, but then self-healing, self-protection, etc. occurs in an autonomous way or automated way. If some pathway gets somehow degraded, the system reroutes for you. You don't have to intervene. This is actually one area where you should get benefits. And of course, you need agents that are functionally versatile while also following some form of protocol. So it's a reiteration of the second bullet point. From an agent perspective, rather than talking dumbbells, you might find that a little bit too abstract. Here's a depiction of this combination of functional plasticity and functional redundancy that you find much more in engineered or potential engineered system, where you have an agent that somehow might have functional modules. It's able to interface with others, so that's on the right side, in some way or form, and protocols help you, so standards, etc., common language. So this would be systems where you have common language to help you in interfacing or interoperation. And on the left side, somehow, you are able, when, let's say, service demands come to fill a number of different requests. That would give you this functional redundancy. Obviously, this is where we got inspired. We didn't discover degeneracy. The biologists have done that. There's many more systems than the ones listed there, because also in medicine, cancer, work, ecology, you find also degenerate design prevalent in biology. The human body does not waste resources just because tasks change. So there's a lot of ways you can, when circumstances change, still adapt and actually make use of your systems. Metabolic pathways is probably a prime example. When you get sore muscles while you run, where you do metabolism, if you're oxygen deprived, you do it in a way, where you don't need as much oxygen, and it's a different the pathway is used for other purposes. In engineered system, you find actually that what I've been talking about is often frowned upon in good system design, because there is actually the endeavor to have systems simpler. So in axiomatic systems engineering, simplicity is defined as one component performs one function. That's a good design. Now that means, of course, if you follow those principles, you don't get the benefits. However, there is actually there are examples in also human design systems, and the domain Fred and I work in defense is one of those. And I'm here already giving you an opinion. The reason why we see in military forces actually degeneracy-based design is, number one, military forces have to deal with very unforeseen and unplanned variations in a very highly demanding domain, where when you can't cope with this change, you might die. So you're highly motivated somehow to be adaptable and robust. And actually military force, humankind has been involved in warfare for as long as probably humankind exists. So it has actually evolved. Those principles in how you go about designing force have evolved. The problem, though, is that administrators now come in and start wanting to make changes in design principles. They say, this offensive support function that this naval gun can do, that your Joint Strike Fighter can do, that your howitzer can do. Why do you have three systems that do this? One should be enough. The reason for this is probably because it has evolved this way, that you build this plasticity in the system. Militaries also use much more modularization in their platforms. I haven't seen, though, that they really use it for this adaptability, but obviously it's easier to change out the module. It's cheaper and easier. You keep your base platform. In Fred's domain, but I don't go into, there's also in the organizational domain, in the military, developments of using these principles. I mentioned already software-defined systems. I mean, one that is very, very important, Androids, iPhones, etc., and human organizations. I just mentioned the third bullet point in terms of opportunities before I wrap up. That I mentioned already. You can actually ask this question: how can I make teams more innovative? People normally say we need more specialists. If you want to make actually, if you want to take advantage of what I was talking about, you might actually see that there might be benefits of people that are multidisciplinary. Not everyone should be, but if you inject into teams some people with multidisciplinary skills, and you have many multidisciplinary teams, you get actually these benefits from this network buffering, and therefore also potentially into adaptability, and you can do this. All right, what did I talk about? And I mean, so the key for me, if there's nothing else for you to take home today, the topology of this mapping of design to function is an extremely important aspect in complex systems design. In particular, if you're interested in building robust and/or adaptable systems. This is something that's often forgotten. People talk about the components, but they don't talk about the functions, and let alone do they talk about how components map to functions. There's a lot in there, and I indicated to you there's also still there's more research that can be done in there, because we have not discovered everything that sits in this, that's encoded in this topology that actually matters really for robustness and adaptability. I showed you pretty much a fairly comprehensive model where we showed that degeneracy-based multi-agent systems are much more able to adapt, evolve, innovate, and that they are more robust to this unknowns, to unexpected change. And network buffering is pretty much quite important mechanisms that provide you with this robustness. And one thing that I didn't mention enough, you can also see now how you can build in redundancy into systems without actually adding extra components. I also mentioned degeneracy-based design is underutilized in engineered systems. However, there's many opportunities, and I've given you at least some characteristics, and you have to look through them again to actually look for, if you know what degeneracy is, you can actually see it, and you can see opportunities. And that's pretty much why I'm no longer doing operations research when I got promoted, but my research program is pretty much using exactly this now in the technology domain area. Now, how can you move from something that's on the left, which is a typical example, a representation functional space of an engineered system, to something on the right that looks more like a biological system? I mentioned here we have 3 points. Inject generalists, multidisciplinary people in science. If you're in science discipline, think about how you are open, how you enable exchange, that everyone can understand, and promote functional facilities. So don't only hone in on specialists. They are very important, but you need people who are also able to transfer knowledge across disciplines. That's pretty much it. I should at least acknowledge my collaborator, James Whittaker, did all the work. But we started the work with at the University of New South Wales, Canberra, in Hussein Abbas's group, and then we continued this collaboration, completed it in Shin Yao's team with Shin and Philip Rothhagen, who's now moved to Australia, as did James again. Anyway, I'll leave that with you. I've talked far too long, but if there are any questions.
Okay, well let's. Okay, RMIT, any questions?
Why can't we all have the same phone charges?
So, what I was just want to unpack something about in your set of environments, which is the sort of the uncertain futures, my understanding that you're testing a fleet mix against, if that's the case, and then in the sort of middle slides you sort of introduced a shock to the evolution process, but to me that seems not the same thing as a unseen environmental thing, which
That's
would
correct,
be coming
yes.
through your E, not the generations of the evolutionary program.
Sorry, no, it comes through E. I mean, so the shock was a different E environment, but where you're right is, yeah, what we did look at, we only looked at environments where the task types stay the same. So if you're talking about, yeah, for instance, functions that you haven't thought of, yeah, then the model did not explore that. This is why we talk about, yeah, one neighborhoods, yeah, and neutral networks where, yeah, you can actually also now access potentially new domains that you hadn't thought of. And the bigger your neutral network, the bigger typically becomes also your one neighborhood. That's a quite natural thing. So, but you're right. The variations that we did, because we said what we kept as a constant, and that was merely so that we can compare the different designs, is that the fleets are always in principle able to meet all the demands that's imposed by the environment, even if there was a shock change to the environment.
And then importantly then, it's really you're optimizing against a deterministic future, really. Because E is constant generation to generation, or is E moving around generation to
E
generation?
is moving around, sorry, the E is moving around in a random walk, but I mean, so the types of task, yeah, is known, yeah, but what changes is essentially how much your level of demand changes, yeah, so it's incremented and decremented, and can actually, it could well be changed to something where all your demand comes only from two tasks.
Yeah, and that's,
yeah.
from generation K to K+1, those demand patterns are varying. Or is E, although it has, this change from time step to time step, still the same in generation 10, 11 and 15 and 3000 in your evolutionary program?
No, okay, it depends on, different experiments. So the one where we showed the robustness, I mean, so you would, so you change the environment and then you run your evolutionary computation for the fleet to adjust. Then you change the environment, yeah, and you use and you allow, yeah, your fleet to adjust. So you start, but what you keep fixed is, yeah, whether you have a purely redundant fleet, yeah, and the purely redundant fleet, because it's constrained, cannot, even if you allow it to adapt, cannot adapt well to those changes. So that's some of the graphs used that others used. Other experiments we did, we actually constrained, yeah, how many evolutionary changes you could make, and they were consistent with these results. Yeah, you get with degenerate systems, you get much quicker, even if you constrain your optimization to say, I'm only allowing you to go through 10 steps in your mutation, a crossover mutation. Yeah, you still get pretty much most of the robustness advantage that you have from a fully optimized fleet.
Mm-hmm.
Does
Do
that
you have
help,
any
Simon?
else?
Or is that enough?
Starts on it, and Moshe had a question. So.
Not really a question, just a comment. I don't think.
Can't hear you, Moshe.
Oh, okay, can you hear me now?
Yes.
Okay, just a comment. I don't think that the term unknown unknowns is very useful here. I think that you should think about another term that will do justice to what you're doing. You cannot deal with unknown unknowns.
Yeah, I agree. I was using that more to at least hint towards why, but you're right. I should not have used it to an educated audience. Yeah.
All right, well, I'm quite conscious of the time, folks, so if there are no more questions from Melbourne, we'll ask our questions here offline, I think.
Okay,
All
thanks,
good?
Amy. Thanks, Axel.
Okay. Thanks, Simon. Thanks, all. Thank you.
Thank you.
All right, we'll see you later, folks. My question was going to be, say, in the vehicle fleet case, how sensitive is it to inherited characteristics? So I'm thinking